Okay, so last time we talked a little bit more about linear programming. Basically, we're going to be done with that for now, or at least the sort of standard algorithms where maybe you're given some collection of half spaces and then you want to solve some LP type problem subject to those constraints. And we're going to move on to some related questions about polytopes. So this is basically going to be the start of the higher dimensional version of the stuff that we've already seen with 2D convex hulls and convex polytopes. But before getting too much into the details of how you go about constructing convex polytopes in 3D or 4D or whatever dimension you care about, we need to say a little bit more about the topology and geometry of polytopes in higher dimensions. Because unlike in 2D, it's actually quite a bit more complicated. So today, the goal is combinatorics and topology for higher dimensional polytopes. And this is just going to be a sort of lightning survey of some results. We'll prove a couple of things that are easy, but probably more things will probably be left unproven, and just you can ask or Google it later if you want to try to figure it out for yourself. But the goal for today is just to give you some of the highlights of what is out there. And most of these proofs, even though we may skip some of them, are actually quite accessible. So they're pretty easy to read and understand. You don't need a lot of advanced mathematics to really get into any of this stuff. So even with just the tools that you already have in this class, this is all quite approachable. So the central concept that we're going to be talking about today is a topological idea called a cell complex. And the reason we need to bring all of this up is that when we want to start doing operations on polytopes, the boundary of these polytopes isn't going to be something easy in general, like a little graph or some sort of circular linked list, right, as we would have in 2D, but it's going to be some higher dimensional structure. And so we need to think about how we can represent these sorts of data types and then how we can compute with them. And we'd also like to understand some of the combinatorial properties of these higher dimensional graphs. So the basic idea is that we're going to try to understand these cells on the boundary of a polytope. And the way we're going to do this is with a concept called a face. Right? So a face, not to be confused with a facet, is something like a generalization of a vertex, edge, or triangle inside some graph. So this is the first concept. So we have a face. Right? So here's the idea. We'll say let some polytope P contained in affine space be a polytope. All right. And let H just be a half space. We're working in affine space, so we'll write it like this. CTX less than or equal to C nod. Be a half space such that P is completely contained inside H. Then a face of P is any set of the form P intersect with just the boundary line, right? So we're going to basically take the set of all x such that C transpose x is equal to C naught. So here's sort of a picture. Imagine we have a triangle like this. Maybe it's filled in. we take some half space here, which intersects it exactly on this edge, then this set right here is a face. That's the sort of idea for what's going on. So examples. Here are some quick examples here. Well, the empty set is a face. It is always a face, right? So we have this trivial face. So is P, because we could actually take the set 0 dot P less than or equal to 0, right? Where this is just a vector that's all zeros. So if we allow for these sort of trivial half spaces that contain the entire affine plane, then the polytope becomes a face of itself. So it's fine. Right. And more generally, if we have any face, then the dimension of this face is just going to be the dimension of its affine hull, in the same way that we can define a dimension for a polytope. So we're going to say for any face, dimension of a face is the dimension of its affine hull. So this is just as a bit of notation here. We'll write the dimension of F is equal to the dimension of the affine hull of F, right? So far so good. So we can kind of map this notion of a face to various concepts that we already know from graph theory. So for example, let me clear out a little bit of space here. So we'll say, let's write dimension of face here on the left, and then we'll put down its common name, or maybe what you've seen before here on the right. Make a table. So if the dimension is 0, then we say that it's a vertex, right? Similarly, if the dimension is 1, it's called an edge of the polytope. This continues going down for many levels until we get to d minus 2.
Slightly darker marker, maybe. It's a little bit hard to see.
Yeah, they're all kind of dead. Let's try this blue.
I have someone that knows more. Well, that's good.
All right, we're going to work with this one then. So d minus 2 faces are called ridges, and d minus 1, we already know these are called facets. Right? Note that it's a facet, not a face. Right? This is just a bit of notation there. By convention, we're going to define the empty face, which is just this, null set or whatever, to be dimension -1. So the dimension -1 face is just an empty set. There's only one of those, and it's unique. And that's the basic idea. So, okay. Faces satisfy a couple of different axioms that I'm just going to quickly write out over here. So erase some of this stuff. Reclaim space. All right, so these are just a few pretty easy to check things. Actually, maybe first I should draw a picture of what a face looks like for a polytope. So here's sort of, right, let me do this. So imagine I just have a square. All right, so here's what the faces look like. So we have this sort of tower. So first we have the entire square itself, which is going to be 2-dimensional. And then this thing is going to contain a bunch of different edges. So we'll have one for the left edge, one for the bottom, one for the right side, and then one for the top. And then each of these things, there's going to be a vertex here for the lower left, a vertex here for the upper left, vertex down to the lower right, and vertex to the top. So we'll just call these things V0, V1, 2, V3, So that connects V0 to V1, V0 to V3, V3 to V2, and V1 to V2. And we'll write these guys and say V0, V1. We'll draw it like this. V2, V3. All right. And there's this containment relation. So if we look at it, this large face contains as subfaces each of these edges. And then each of these edges contains some vertex, or some pair of vertices as subfaces. So this contains there. That one, I guess, contains there. And this one. Right. And then at the very bottom down here, we have an empty set. So these will be 1D, and then these are 0D, and then down at the very bottom, we have a negative 1D face. So this structure here is sometimes called a face lattice. And what we can see is that, first of all, in a convex polytope, every face of this polytope is also a polytope, just usually one dimension lower. And that the faces of any polytope are strictly contained in the original polytope. So let's start writing these down here. Erase this. So here are some observations. So first, every face is a polytope. 2, the face of any face are contained in the faces of P. Maybe went over a little bit there. Another observation is that if we take any two faces and we look at their intersection is also a face. So we'll say the intersection of any two faces. A face. And another one is that any face is trivially equal to the intersection of P with the affine hull of the face. And if we think in terms of the vertices of a face, these are basically the extremal points. So we can think of the vertices as just all the zero-dimensional faces. So the vertices of any face are equal to the face itself intersected with the vertices of P. So in this way, we're starting to see that there are some rules these faces have to obey, right? And in particular, the two which are probably the most important are actually numbers 2 and 3. And so we can use these two rules here to generalize this idea somewhat so that it's no longer tied specifically to polytopes, and it now becomes a somewhat more abstract combinatorial concept that we can now work with using tools like algebraic topology. And this is the idea behind a cell complex. So that's actually what we're going to spend most of our time talking about today. So the basic idea behind a cell complex is that it's something like a higher dimensional version of a graph. So in graphs, we have vertices and we have edges, and then it just stops. So there's nothing after edges in a graph. But if we just keep iterating that idea, going beyond vertices off to maybe like little surfaces that we'd glue together, and then from surfaces to little solid objects and volumes that we glue, and so on up into higher dimensions, then the resulting structure that we would get would be a cell complex. And cell complexes show up in a lot of physical applications. So in engineering, maybe you've seen like finite element type meshes where you would have like a bunch of different faces all connected together, something like this, right? And then these little bits would all be used to approximate some larger shape by chopping it up into tiny triangles or tetrahedra. Or if you have, say, like a map, this is maybe some geographic region partitioned into tinier pieces, then you could think of each of these countries or regions in your map as being some cell. And so these sort of cell complexes show up in a lot of geometric applications. All right, so that's kind of the high-level idea of what these things are. And I'll now give you the definition of what a cell complex is. So here's the basic concept that we'll need for polytopes. So for polytopes are a polytopal cell complex, but we're just going to call it a cell complex for now. Say a cell complex. It's basically a bunch of lower dimensional polytopes glued together. That's all that it is intuitively. So a cell complex X is a set of polytopes such that one, any face of a polytope in X is also contained in X. So we'll say for any f in X, all faces G contained in F are also in X. So we're just going to say that if we take any face, we can just drill all the way down and explode it into all the tiny little faces that it's made out of, and they all have to be contained in there. And more importantly, the intersection of any fg in X is contained in a face of f and g, or is, not is contained, we'll say is a face. Right, just the correct way to write that. Okay, so what this means is that we have maybe some collection of polytopes glued together. They'll have to be convex because they're convex polytopes. So they can meet maybe at edges or vertices in some way, and they would all be pieced together. So the key requirement is that if we look at any pair of polytopes, then they would have to meet at some common face. So in 2D, they're always going to be glued together along their edges. So if we're given a cell complex, we can split it apart into different pieces based on its dimension, on the dimension of each piece. So we can define things like vertices, edges, and faces, and so on of a cell complex as we would for a graph by splitting the cell complex apart. Right? And so these graded pieces, right, are called the skeleton of the cell complex. So we'll say, given a cell complex X, the K skeleton of X is the set of all k-dimensional cells in X. So I'll write it like this. So we put these like little parentheses around k, all right? And this is the k skeleton of X. And it's just the set of all of these faces F such that the dimension of F equals k. All right. We're also going to define the underlying space of a cell complex as the union of all of the cells in the cell complex. And the standard notation for this is actually pretty terrible. It's written with a set of bars around the space, so it looks just like set cardinality. So I'm going to write it a slightly different way for today's lecture. And if we have to change it later on, I will try to make it clear if we do that. But just for now, we're going to write it this way. So we're going to say the underlying space, and we'll write it as maybe capital U, right? Where will I put it on the board? I erased the top part. So underlying space. And today we're going to write it as U of x is just equal to the big union of all of these cells, F and X, all glued together. So we can think of this as we're just going to forget that it was a cell complex and then just smash everything together, and now we're back to a set again. And so with this concept of an underlying space, we can say the following, which is that we have this tower of the empty set is contained in the negative, or is actually equal to x negative 1, which is contained in x0, which is or this should actually be u, right, which is contained in u of x2, and so on, all the way off to u of xd, which is equal to x. Well, in the case of a polytope, it'll be equal to the u of x, right, for a polytope. So this is for polytopes. We have this chain of underlying spaces, so they're all contained in one another. So every time we go down a dimension, we're left with some more cells sitting around. So, okay, so that's the simple idea there. So here are a few other things that we would also like to define. One of which, and this is why I didn't want to use the standard symbol, is that I'm also going to introduce another piece of notation here, which is this concept called an F vector. And it's actually a really simple idea. We're just going to count the number of elements in each of these skeletons here. So this is basically a vector of number of bases in cell complex. So here's the idea. It's just some vector f sub negative 1 of p, f sub 0 of p, and so on, all the way up to f sub d of p, where f sub I of p are f sub I of x, not p. Whoops. Right, talking about a cell complex here. F sub I of x is just the cardinality of the I skeleton. So we can think of this as just the number of I-dimensional cells. So, for example, f negative 1 is always 1 because every cell complex has to contain this empty set. Similarly, f0, well, this is the number of vertices. And if we go all the way on up, well, we're always going to have fd equal 1 in the case of polytopes. And then fd minus 1 is actually the number of facets in the polytope. So what does that mean? Well, here's an immediate observation. If we want to do convex hulls of higher dimensional polytopes, they're always going to take at least f sub d minus 1 time because that's how big the output is. So here's the sort of simple conclusion, or it's maybe just obvious, right? The size of the convex hull is fd minus 1, right? Because that's basically the number of facets that we're going to end up with at the end of the day. So if we can find some way to express f sub d minus 1 in terms of f sub 0, right, then that will give us a good way to estimate the size of a convex hull in high dimensions. And that's the goal that we're going to try to work on for now, for a little bit. And there will be a couple of leaps here and there. I'll try to point out where there's basically something that you'll have to look up. But this is the idea, is that we'd like to compute some bounds on these f sub d minus 1. And generally bounds on the size of all the elements in this f vector, because a lot of algorithms in computational geometry are going to have their complexity bounded by how large this will be. So maybe we're going to be given one of the components of this vector, and then we'd like to bound how large the other components are going to be in the vector. So that's the idea. And so this all is for general cell complexes. So, okay, and I should also say that in the case of polytopes, we're usually going to just have arbitrary polyhedral cell complexes. So they're just going to be polytopes glued together. However, it turns out that it's actually quite difficult to work with arbitrary polyhedral cell complexes, or at least it becomes a little harder to prove things right away. I mean, the results that I will say today will hold in general, but to speed up some of the derivations and some of our calculations, we're going to consider a restricted type of cell complex where all of the cells involved are simplices. So that is, they're either going to be vertices, edges, triangles, tetrahedra, and so on in higher dimensional spaces, right? This may seem somewhat contrived, but actually, if you take an arbitrary V polytope, then it's almost completely certain that what you will end up with at the end of the day when you construct its convex hull is a simplicial complex. That is, a complex whose facets are all simplices. Here's a simple argument for why it is. So here's the sort of theorem. Most V polytopes have simplicial convex hulls. All right, so here's a sketch of how you prove this, which is, okay, take any V polytope which happened to be not a simplicial V polytope. So just say take any V polytope with a non-simplicial hull and select any non-simplicial face F. So all vertices on this facet F are going to be coplanar, right? Well, this is kind of a degenerate case, right? Because there's one of two situations. Either on this facet, right, which is going to be a d-1 dimensional plane, right, we're going to have greater than d-1 points, or greater than d points, which are all going to be coplanar. So here's sort of a picture of this. Imagine in 2D, right, I have, or well, let's say that we have something in 3D. So suppose I have 4 points which are on a plane. All right, well, this is pretty unstable. If I perturb any of these vertices by a tiny amount in or out of the plane, it can be as small as you'd like, just like the tiniest epsilon, then they're no longer going to be coplanar, right? And the result is that then I'm going to end up with some simplicial facet that's going to look like this, right? So the result, right, is if we just perturb vertices by, I don't know, some small amount, then it is simplicial. So the corollary is that if we start from so the conclusion is that if we start from a V polytope and then just randomly take convex hulls, if it was in general position, then it's always going to look like a simplicial polytope. So from sort of a numerical or practical perspective, you could argue that maybe it's enough to just think about simplicial polytopes. But it turns out that this theorem was sort of written for V polytopes. So if you try to do the opposite sort of thing for H polytopes, it turns out that most H polytopes are actually not simplicial, but rather co-simplicial, which means that they're actually dual to a simplicial complex. So simplicial complexes are pretty useful in a V polytope centric world. And they're the ones that we're going to start doing work on today, because it's easier to just get started and start proving some things, even though the general case is really non-simplicial complexes. Right. So, OK. All right. So what do I want to? Right. Simplicial complex. OK. So here's the real neat thing about simplicial complexes is that we can define them geometrically, as we did for the case of cell complexes, but it's also possible to define them combinatorially, like we did with a graph. And so this is the definition for an abstract simplicial complex, which is, in some sense, a combinatorial model for what goes on inside a simplicial complex. So this is the idea. And with this, we can do algebraic computations that would allow us to prove various things about the F vector of a simplicial complex. Simplicial. So this is the idea. So we'll say given a totally ordered set V, which is going to basically be the vertices of the polytope, an abstract, and we'll kind of drop the term abstract when we're working here because it's almost always going to be an abstract simplicial complex. Complex X, some subset of 2 to the V, right? So this is the power set of V, okay? Is a finite collection of sets such that for all F in X and G in F, G is in X. So this is pretty much the same definition that we had before, except now we're just talking about finite sets. So here's maybe a mental picture of how this works. Imagine that we have, say, 2 triangles here. We'll have vertices V0, V1, V2, and V3. And suppose we have these triangles filled in. Then the simplicial complex that would be formed by this pair of triangles would look like we'll have the sets V0, V1, V2 for the first triangle, V1, V2. And then we have the set for the other triangle, so it's V1, V2, V3. And then we have all the edges, which have to be contained in here. So we have V0, V1, V1, V2, V0, V2, V1, V3, V2, V3. And then we have the vertices itself, so we have V0, V1, and then we have the empty set. All right, so that's the basic idea here. So we don't have any concept of space or geometry here, but it turns out we can take any abstract simplicial complex, and it's pretty easy to turn it into an actual subset of Rn. Because here's all you have to do, is that you basically take each of these vectors, and then you just stick them in a crazy high dimensional space, right? So if you have n vertices here, we're going to stick it in R to the n, right? And then for each vector, we're just going to map it to one of the basis vectors there. And then each cell is just going to be the convex hull of one of those basis vectors. So it's pretty trivial to transfer results that you have on an abstract simplicial complex to results on a regular simplicial complex, because it can be transformed into it by this automatic procedure of blowing it up into a high dimensional space. And you can always project that higher dimensional version down to a lower dimensional version, or stick your lower dimensional one up into the high dimensional setting. All right. So that's kind of the picture. So we can work with these abstract simplicial complexes and do some calculations with them. So one of the first operators that we would like to investigate here is this concept of a boundary of a subcomplex. So here's sort of the idea, is imagine I take these two triangles here, and I would like to find the boundary of those two triangles, which will basically be the set of all edges which are incident to just those two triangles and nothing else, right? So we would like to, say, given those two triangles, find these edges here, right? So this is sort of the concept that we would like to try to articulate. The reason that we're going to care about these boundaries is that it's going to be very useful in defining some invariants, right? Not to give away too much at this point, but we would basically like to have some map in a way that allows us to say, given some subcomplex, pull out all of these cells which are just incident to it on the boundary. So we remove the interior edge here, and then we're only left with these exterior points. So one way we could try to make this maybe more precise is imagine that we basically take each triangle individually, we explode it out to get these boundary edges, and then we just go through and then join them all up together. And whenever we double count an edge, we toss it out. Or if we thought of maybe in another way as like assigning some charge or value to each of these edges and triangles and vertices in our simplicial complex, then we could imagine that what we're doing is basically going to be summing up all of these values, and if they cancel, then we'll just toss that edge out and we'll be done. All right, so that's the idea here. So one way to keep track of these values is with a concept called a chain complex, or a chain, right? So here's sort of the simple idea behind a chain, right? So we have this related notion of a chain. A chain is just a function, we'll say it's some c, in the space of real valued functions on the complex X. All right, so we'll basically say that for every cell in X, it assigns some value. That is, that the type of C is X maps to R, right? In the same way that 2 to the V, right, is sort of the power set. Here we're looking at the space of all real valued functions on a chain. So we can think of this as a vector space where the basis elements of the space are the cells in the cell complex. So for example, if I have a point here, I could have another point here, and I could add them together and maybe connect them with a line. And so the sort of map that we would like to have here is some map that we're going to call boundary. We're going to feed it a line as input, and then what's going to pop out is, say, a positively charged left vertex and maybe like a negatively charged right vertex. They're going to be oriented in some way. Or similarly, if we have some network on this chain, we can imagine that we're going to assign an orientation to each edge. So we'll think of this edge as basically being oriented in this direction. And when we sum up these oriented edges, we would like to get some output value, right, which will be oriented in this way. I don't know. This is maybe seeming slightly vague, right? But this operator here is sometimes called a differential, and in some sense it's sort of like a generalization of a derivative that you can think about. So the basic idea is that this derivative operator here is going to take a chain as input and give us a chain as output. That's the idea. So we're going to have this thing, delta, which will take a chain. This is some function on the cells, and then give us a new function defined on the cells. OK. Right. So how do we define this? Well, the basic idea is that we can define what delta does to each cell individually. So if we take any basis function that's defined on a single cell, and then we apply delta to that basis function on the cell, then we can just expand it in terms of the rest of the basis functions, which will pop out, and that gives us a complete description of what delta does. So how does this work? Well, we're going to use this total ordering here that we have on the set of vertices, and we're going to just sum up over all of the elements. So here's the idea. So this function here is just, we're going to think of this as the basis function that's for the face f. So this is a set of vertices. And we're going to write this as the sum from I equals 0 to n, where f is equal to this set v0, or v1, v2, v3, etc. up to vn, with v0 less than or equal to v1 less than or equal to so on less than or equal to vn. Actually, I left out the 0. So this is going to be -1 to the I times the indicator function of f with the ith vertex in f removed. So what we're doing is we're just iterating over all of the sets that we could remove one element from f, and then summing them all back up together. All right. So I already drew one picture of what this looks like. I'm going to erase this top part here. So if I have, again, some line here, we'll write this as v0 maps to v1. Then this is going to spit out, say, a plus times v0 with a minus times v1. Or if I take a pair of lines chained together, so v0 maps to v1, maps to v2, and I apply this operation, well, I'm going to get 1 plus v0. Right, so this will be plus. Then I'm going to have a minus v0 on this end and a plus v0 on this end. So those are just going to cancel out. So I don't get a v1. And then at the end, I'll have a minus v2, right, because of the other term. Right, so the v0 goes away, and I'm just left with only the boundary of this thing. Right, so you can think of this as just like a notational trick. And if I want to recover the actual subcomplex which represents the boundary, I just have to take the support of the resulting chain. And then that'll give me the underlying space of the resulting cell complex. Similarly, if I do this in higher dimensions, I get basically what you would expect. So imagine I have a triangle here, and I have this cell v0, v1, v2, and I compute this boundary operator. Well, I have to go through and then just figure out what happens as I delete each of them. So I should get basically this edge oriented here for the v1 to v0, or v1 to v2, an edge oriented this way, and an edge oriented this way. So one way that you can often draw triangles when you're talking about them in this sort of framework of simplicial complexes, or when you're talking about chains, is to draw like a little spin on the triangle, so you have some orientation to it. So when I compute the boundary of a triangle, which is spinning in this way, I'll get, actually, I should have drawn it like that. Then I'll get these output edges here. All right, so that's kind of the idea for how this works for cell complexes. And so if I computed the boundary of, say, a triangle that was oriented like this, and another triangle which was oriented like this, then the resulting boundary edges, which I drew in green, will be oriented along these spins here. All right. So that's the basic idea of the boundary. And it has a couple of neat properties. So one of them is that if you iterate it twice, you get 0, right? So if you take the boundary of these two triangles, you get one of these green, circulating vector fields, right? And if I take the boundary of this again, well, what will happen is that this vertex here will cancel with the other, edge of this line here, and the result will be 0. And you can prove this formally by just, looking at the equation that you get, right? So if you just write the boundary of the boundary, so the boundary of any chain, of any cell, right? You can just do it for whatever cell you pick. This is going to be, the sum from I equals 0 to n, -1 to I, followed by the sum from j equals 0 to I minus 1, -1 to the j, 1 of f set minus vi vj plus the other elements. So I'm basically summing all the way up to I, and then I'll sum from I all the way up to the rest. So from j equals I plus 1 to n of -1 to the j again, set minus vi vj. And, well, there's not a lot of space on the blackboard, but basically if you just rearrange these terms out here, so you can group these two terms together and then these two terms together, and then use the fact that vi vj is equal to vj vi, you can then change the indices, cancel the sums, and what you end up with at the end of the day is that boundary of boundary for any of these basis elements is equal to 0. Right? So the conclusion to this, by purely formal means, is that for any input cell, you always get 0 when you feed it in again. So so we have this linear function called the boundary operator. And, well, what do we know how to do with linear functions? We know how to compute their null space and their column space, right, or their image and kernel. Yeah?
Sorry, quick question. So then, if you just did the boundary of the boundary of, say, the line segment, how does that end up being 0?
Yeah, so basically if I take a point, right, and I compute the boundary of that point, then I'm going to get basically an empty set element, and it'll just die, right? So that goes away. So, yeah, that's pretty much what happens. So if I take the boundary of this one, I'll actually get a plus empty set, and I'll get a minus empty set here, and then it'll go disappear,
so
actually.
What about the triangle?
So again, what will happen is for each of these vertices, I have a plus v0 from this edge and a minus v0 from this edge. And then when I sum up those, I get a negative for that when it goes away. And then for all of them, they all disappear. You've probably seen some variation of this operator maybe in an analytical setting for vector fields. So, for example, the divergence of the curl of a vector field is equal to 0, which is basically the same thing as what you're getting here, right? So if you take the gradient of a vector field, or the gradient of a scalar field, then that vector field is going to basically be divergence free, right? Is another way to think of it. So it's actually related to the same type of result, right? It all fits into this broader mathematical or topological theory. Right. So, we have this operator called the boundary, right, which basically we toss in a chain, and then out pops another chain, right, which we're going to think of as the boundary of that chain. So we can think of the vector space of chains, right, as just a vector space, right, and we can then talk about subspaces or flats within this vector space. So this operator here, which I'm going to have to erase around a little bit, actually splits this whole space into a couple of subspaces, right? So we have the image of the boundary operator, which we can think of as actually boundaries of some chain. So we have these boundaries. And then we have the kernel of this operator, which are things which, if we computed the boundary of them, we'd get 0. And these things are called cycles, right? So they're kind of like bubbles in the space. So we have two types of chains. So we have boundaries, right, which are chains which happen to be contained in the image of delta, right? So these are basically chains which are derivatives of chains. And we have cycles, right? And this is the kernel of this operator. And these are chains which have no boundary. So in graph theory, if you've ever heard of like a cycle, it's exactly the same thing, right? And if you have sort of the terminal vertices, those are actually like one example of a boundary within a graph, right? So these are the two basic operations. And so we can think of these cycles in some sense as being like a bubble or like a loop. So in 2D, they're always going to look like some sequence of vectors marching along like this, or some linear combination. So I could add in another chain, maybe oriented another way here, right? And so these are actually vector spaces, right? So they're basically any linear combination of these chains are going to be contained in these two subspaces of the space of all chains, which are the set of all real-valued functions on this cell complex, right? OK, and because of this result here, right, we know that the differential of a differential is 0. If we have something that's in the image of delta, right, then we automatically know that it's also in the kernel of delta here, right? So the conclusion of this, right, is that the image of this map is contained in the kernel of this map, right? Or, in other words, every boundary is a cycle. Surprisingly, or maybe not, I don't know, the converse is not always true in a general cell complex. So in the case of, but the forward version is definitely, right? So if you take any boundary, if I take any cell here, I should probably pause to emphasize this point, and I compute its boundary like this, then this resulting set of chains over here, or this resulting chain that I get, looping around it, is automatically going to be divergent 0, right? And that's just what we already proved. So I'm basically saying the same thing here that I already said, but just using this other language here. So boundaries are all cycles, right? Which makes some sense if we're going to think of boundaries as being like a bubble. So you can imagine that if we took something and then we deleted it from the cell complex, there'd be this leftover bubble floating around out there. And then that oriented bubble, if we collapse it again, is just going to be a cycle, right? So the cycles are, in a sense, the bubbles that are floating around in this mental picture. So now that's the easy direction. The hard thing is that it turns out for polytopes, in a cell complex, every cycle is also a boundary. This is not true in general, right? But the sort of high-level picture for why this is the case is that if you imagine, like if you had, say, like a giant sphere here, then if you fill in the interior of the sphere, you can cover this final like loop, right? So in a sense, like every cycle is going to look something like a sphere where you just deleted the interior of the sphere and then assigned an orientation to the boundary of it in some way. And so if your space doesn't have any holes in it or any bubbles left, then there is going to be a situation where every cycle has a corresponding boundary that matches to it. So every cycle is the boundary of some chain. That's not true in a general cell complex, but it is true in the case of polytopes, when we happen to include the polytope itself as the final cell, right? So I'm going to punt on proving that, and I may revisit it later in one of the special topics if we have time permitting. So I'm sorry to let you guys down and not give you the full featured proof of that statement. But instead, I'm going to use this fact, right? So this is sort of the proposition, right? Because it's a theorem without any proof. So here's our proposition. Maybe you can just think of this as an assertion. We'll say for polytopes, every cycle is a boundary. Not true in general, but just for polytopes, all right? OK. So what can we do with this? So here's where we now connect all of this back to f vectors. Is because if we look at what happens to a chain whose support happens to be only k-dimensional faces, then when we feed those k-dimensional faces into the boundary operator here, we're going to get k-1 dimensional faces out. So here's one way to think about this, is that OK, if we compute the boundary of the k-skeleton, then this is going to be contained in the k-1 skeleton. All right, so this is the idea. So we look at the chains which are supported on k cells. The result is going to be chains that are supported on k-1 cells. So what this means is that we can basically split this space here into a direct sum of orthogonal subspaces, right? One for each of the sets of chains. So the idea, right, is that we can take this space here, and then we can grade it, right? This is the idea of a grading, right? We can grade it into this Rx minus 1, direct sum with Rx0, and so on, all the way up to Rxd. All right. So these two spaces are identical. All I did here was I just took the functions here, which were defined on arbitrary dimensional cells, and then I just split them up, just as a notational convenience into, the -1, 0, and so on cells, all the way off to the full D cell, which is going to be the entire polytope. OK. Now, here is the idea. If we have this, then we can also then split apart the images and kernels of these cycles. All right. So here's what we're going to do. We're going to define bi, which is going to be equal to this boundary operator applied to Rxi plus 1. All right, so this is basically going to be some subvector space of Rxi. Right? And similarly, I can define these cycles, Ci, which are going to be they're going to be in the co-boundary, right? So they're going to basically be the kernel of this operator, delta, applied to are restricted to the subspace R of X sub I. All right. This is kind of the idea here, and this is also going to be, again, contained in X sub I. And so we know from this proposition and this proposition, right, that these two vector spaces are isomorphic, right? So they're equivalent vector spaces. In fact, they're actually just equal. So we have that bi is equal to ci, right? And in fact, that this actually covers the entire space of all of these cells here. So this is the consequence, is that we can actually use these things here, then, to calculate what happens to f vectors, right? So if we think about feeding a general chain in there, right, where basically here's sort of the idea, right? I'm running out of a lot of space. I'm going to erase something. I'm going to erase this big blob here because I need more space. So here's the idea, right? So we know that the dimension of R x I is equal to the ith f vector of the or the ith component of the f vector. So we can relate these values of the faces to this result. And then using this concept here, we can basically construct how does this work? Okay, we can conclude that if we take, if we take the boundary operator of the entire cell complex and then feed it through forward, we'll have basically that the rank of this operator delta is going to be equal to what would happen if we sum up all of these things in an alternating series. Right, so this is basically going to be the sum of all of these f i's to -1. I hope I didn't make a mistake here. Okay, I think that's correct. Right, and that if we sum this another way, by counting the boundaries and cycles, then this should also be equal to -1 to the I dimension of bi plus the dimension ci. Right, because the rank, right, so what does the rank mean? It's the rank of an operator is the dimension of the kernel minus the dimension of the image, right? So this is basically equal to the dimension of the kernel of delta minus the dimension of the image of delta. Right, and so what's going on here? Well, I'm using, I think I got an index wrong. Maybe I did. I don't know. Yeah, that should be -1 to the I. Right, so the rank of delta is the dimension of the kernel minus the dimension of the image. Right, and where did that go from? Trying to remember why this isn't. Right, so this should be -1 to the I here. I don't know. Okay, well, this formula here should be correct. I forget what I did to derive it. I didn't write down a note for this. So I'm just going to circle this here. All right, and I'll try to say something about that later. All right. The thing I forget is I don't remember why it has to be the sum of -1 to the fi. But it should be. I know morally that this is correct, but I forgot the exact derivation for why that's true. I will post something about it later. I don't know off the top of my head right now. Right, so okay. Supposing, though, that we have this formula here, then what we can say about these dimensions of the bi's and the ci's is that, no, well, what does this mean, though? If I take, right. No. Here's why this is correct. Right. Yeah. Here's where it's right. Because basically, if I take the dimension of fi, right, well, I can basically take this operator delta here, and then basically this is going to split it into the image of this vector space and then the kernel. So this is basically separating this space here into the perpendicular and parallel components. Right. So the sum of the dimension of the parallel part and then the perpendicular part is equal to the dimension of the entire space, which is right here. So that's what's going on. Okay. Right. So, all right. So I have this formula here, right, which is that I go from I equals 0 to d, negative 1 to the I, sum up all of these things. And what I get is an alternating series, right? And so here's the key thing, is that if I look at this, the dimension of bi, or the dimension of ci, because of the fact that every boundary is a cycle and every cycle is a boundary, means that bi should actually be equal to ci plus 1, right? Yeah. So that the dimension of bi is equal to ci plus 1. So if I write all of this out, I'll get this I is equal to the sum from 0 to d of negative 1 to I, ith f vector is the sum from I equals 0 to d of negative 1 to the I dimension bi plus dimension bi plus 1. Right. So if I write this out here, right, just using the fact that the cycles are going to be equal to the dimension of the boundaries one dimension higher, right? So I now have an alternating series here, so I can cancel out each subsequent bi at the end. And what I'm left with here is I just have the dimension of the 0 cell, right, and then the final dimensional cell, right? So it might be, yeah, you might be right. It might be bi minus 1. But it doesn't change the result, right? I mean, it's just going to be an alternating series because I'm just adding these two subsequent terms, and I'm flipping the sign back and forth each time I add up the next two bi's as I sum up this whole series of all of the dimensions here, right? Now, the upshot of this is that when I sum all of this stuff up, most of these bi's will cancel, and I'm just going to be left with the last two. So I'm going to have the dimension of the dth dimensional, or the dimension of this negative 1 bi, right, plus the dimension of the dth bi times I to the, so this whole thing times negative 1 to the d, I guess. Is that correct? Or negative 1 to the d minus 1, right? Because this should actually go up to d minus 1. Yeah. Yeah, the reason it only goes up to d minus 1, right, is because at the dth term, you can't actually take the inverse boundary of it. So that's why the last two are left out of the whole series. So all right, let's clean this up a little bit, and we'll kind of simplify and cut to the bottom line here. So here's the result, is that if you take the terms in the f vector and you sum them up in this alternating series, you get this number, which is called the Euler characteristic of the cell complex, but in this particular case, the polytope. So we have this quantity here. We'll call it g sub x. And this is defined as the sum from I equals 0 to d minus 1 of negative 1 to the I of the ith component of the f vector. And we know that since most of those b's cancel, this is going to be equal to either 2 if d is even, or if d is odd, or 0 if d is even, all right, just because we have that negative 1 term. So what does this mean? Well, it means that these f vectors have to obey certain constraints. So they can't just be any arbitrary set of values. They have to fit into this particular formula. And this actually turns out to be a pretty useful invariant to check if you have some solid object and you want to verify that it's actually correct. So for example, if we take like a cube and we calculate this f vector for a cube, all right, so we have the following components. So we have 8 vertices. So we have f0 equals 8, f1, 12 edges, right? And then f2 is equal to 6. So if we take the alternating sum of these two things for a 3D cube, we'll get 8 minus 12 plus 6, which, if everything works out correctly, gives us 2, which is fine because we're in a 3D cube, so that's what we would expect. If I take a 2D triangle and look at the boundary of it and then sum up all these faces. So I'll have 3 vertices, 3 edges. Sum them up, I get 0. So that's correct, too, for this 2D planar figure. I can do the same thing with a tetrahedra. So I'll have V0, V1, V2, V3. So I have 4 verts, 6 edges, and then 4 faces. And again, I get 2 when I'm all done for a tetrahedra. So you can do this trick for any polytope, any subdivision of them. It always will come out to 2 in 3D, or in 2D, it'll always come out to 0. And in general, it'll basically come out to either 2 if you're in an odd dimensional space, or 0 if you're in an even dimensional space. So this is the basic sort of invariant that we can define. You can generalize this to arbitrary cell complexes. I'll just say a few quick words about how that works. It turns out that this Euler characteristic is an invariant of a space. So it doesn't matter, in a sense, what cell complex you pick. It only matters the topology of the underlying space in which it's defined. So you can take any space, chop it up any which way you want in any kind of cell complex, calculate this Euler characteristic, and you will always get the same number for that space. It does not matter what space you pick. So in the case of a sphere in 2D, or in the case of a sphere in 3D, you're always going to get 2, no matter how you chop that sphere up into cells. When you chop it up and then you sum these up, you'll always get the same result. If you happen to have, say, a torus, you'll get a different number. And if you have like a plane, you get a different number from that. But it's unique to the space, right? And so for surfaces, the Euler characteristic is sometimes 2 minus the Euler characteristic is sometimes called the genus of the space, right? So it actually counts the number of holes that happen to exist in a surface. So for toruses, you'll get 1. For like a double torus, you'll get 2, and so on, going off to like higher values. And that's the basic idea there. It turns out surfaces are completely classified given their genus, right? So this actually is enough to totally determine the topology of a surface. But in 3D, it turns out that there's actually more parameters to describe what goes on in an F vector or what goes on inside some higher dimensional manifold. But I'm out of time right now, and so we're just going to leave this at that and call it a day.